than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
Hi, we are Walls, Waste Allocation Load Lifter Space Class, inspired by the beloved Pixar movie WALL-E. My name is Emma.
I'm Damian.
I'm Noah.
I'm Mitansh.
And I'm Joshua.
And we are presenting our idea of cleaning up space sustainably.
Space. Since the Apollo 11 launch, the industry has expanded immensely. And with each year, we send up more and more satellites, covering numerous applications from telecommunications to military. But this all started in 1957 with a Russian satellite called Sputnik. But in 1978, NASA scientists Donald J. Kessler and Burton J. Corpellet theorized that with the increasing amount of things that we're sending up, there will be an increased likelihood of collisions between satellites and then the debris that these satellites leave behind. It is this debris that poses an existential threat to everything up there. An example of this is in 2007, a Chinese anti-satellite test doubled the current amount of debris up there. There are currently two big players in this market, astroscale and clear space, but they only deal with larger debris, and they deorbit it, polluting the Earth's atmosphere.
Track, capture, remanufacture. That's our slogan here at Walls. We're proposing the first ever full stack space debris mitigation solution. It's an environmentally friendly end-to-end solution. We're the only firm that captures the debris and remanufactures it into valuable materials in space.
We realized the potential that comes with the debris raw material. So instead of putting it to waste, we will remanufacture it in space to produce a machine that will capture again. And end the cycle of space depollution, instead of burning it in our atmosphere, which causes ozone depletion, by just putting it into a graveyard orbit, we directly address this problem like no one else has done before.
WALLS is an innovative idea that will take space and humanity to the future based on sustainable exploration. Now let's launch into the details.
So there are a number of capture processes which have been proposed for the removal of debris. Since we're targeting debris in the range of 1 to 10 centimeters, we pursued a method which hasn't been done before: sweepers. The sweeper method proposed deploying a structure similar to a shield in space, which moves at a lower velocity than the debris itself. The targeted debris moves at velocities of 3 to 18 kilometers per second. This is defined as hypervelocity, and it would typically annihilate any structure that it impacts. So the solution that we're proposing is to use a modified Whipple shield structure to trap the debris. You can see here, this is a traditional Whipple shield structure. We aim to optimize this traditional structure so that the shield captures the debris instead of just breaking the debris down or changing its direction to re-entry. Ideally, we're looking for high velocity impact with minimum debris and shrapnel produced. There have been several materials which have been investigated in recent years. Now, research by Jing et al. Has found the use of aerogel and fiberglass composite effective in shielding, and it also has better thermal insulation. The investigation is being done using ANSYS Autodin for the numerical solver, and these results are being benchmarked against traditional Whipple shield structures being currently used on the ISS. Due to the low spatial densities of debris in the 1 to 10 centimeter range, the proposed size of our sweeper is 300 meters wide, and to ensure that the debris is collected well, the CAD can be seen on the screen. It's made out of hexagonal panels, which from tip to tip have 1.2 meters in diameter, and this allows easier transport and maintenance of the overall structure panel by panel.
The small fast-moving pieces of debris are almost impossible to detect with our current state-of-the-art methods, which range from ground-based radars to telescopes, and only cover a small portion of our space and only able to detect large pieces as small pieces just go unnoticed. So our proposed method is using optical sensors on our spacecraft and going through all of Earth orbit, being able to track them and create optimal trajectories for it. It can also serve as a avoidance collision for future systems. And without an efficient tracking system, we could end up catching a satellite that we don't want to.
So, how are we going to get to this debris? There are two perspectives to consider. active and passive. The active point of view suggests that the debris be located and then our orbit adjusted to come into contact with the debris. Now, this would be a far quicker and guaranteed method of debris collection, but far more costly, because up in space, the only currency we have is fuel. If, however, we were to use a passive approach, minimizing our fuel use, focusing on the orbital areas with the higher densities of debris, the probability of collision would be high and the fuel use would be much lower. So even though we would not technically be guaranteed a collision, we could keep our sweepers up in orbit for a much longer period of time, allowing for a higher potential of return in the long run. To achieve this, we need to design an orbit and decide on a propulsive method that is capable of long-term burn and high fuel efficiency. Now, let's take a look at the Earth. The orbit we want, we'll start off around here. We're going to go round, sweeping up all the debris in that section. And then we're going to increase our orbit by 300 meters, the exact diameter of the sweeper. We'll then go round again, sweeping that new altitude. And we'll do that until we reach our upper limit of the orbit. We'll go around, and then, having swept that entire area, we'll need to change the inclination, which is the angle of the orbit around the Earth. So, if we have the Earth like this, and the inclination like that, we would need to adjust it to here, and then do another orbit around here, just like the one you see here. And we would continue doing that until we've swept the entire area of the orbital high density debris. And then with that, we can decide upon a propulsive method. For this, electric propulsion is ideal. It has a high fuel efficiency and can burn for months at a time.
Space debris is comprised of numerous different materials. Some of those materials are not very easy to recycle, and others have limited applications in in-space manufacturing. Metals and metal oxides, however, are very ubiquitous in space and are very easy to recycle into feedstock for manufacturing. The recycling process for metal oxides is similar no matter which metal you use. However, focusing on aluminium is attractive because of its use in aerospace parts and its ubiquity in space. On Earth, electrolysis is used to process aluminium oxide into pure aluminium. However, some aspects of this process rely on gravity, which isn't present in space. For example, when bubbles form on the anode of the electrolysis cell, gravity is used to induce buoyancy in the bubbles and remove them from the surface of the anode, making the process continue to happen. Whereas in space, this is not a possibility. Additionally, the differing densities of the materials are used to separate them out. The proposed solution is to use a pump to push the material through the electrolysis cell, dislodging the bubbles and separating the materials out. And we're going to look at different geometries of electrode, different positionings, and different flow rates of the pump to try and optimize this process.
Debris capture is the first step. The second is remanufacturing it into something valuable. Our solution for recycling metal in space is benchmarked by the Mamba process developed by Tethers Unlimited and funded by the Small Business Innovation Research Program. The Mamba process heats aluminium to 670 degrees Celsius and then cools it to 640, using a hot press to form a metallic ingot before machining it into a final part with a 0G CNC mill. However, Mamba's results were not too promising. The remanufactured's metal properties severely degraded due to inefficient heating and cooling. That's where we come in. Once the debris is captured, it's transported to an unmanned space station where it undergoes processing. Our goal is to create a continuous cycle in orbit by remanufacturing parts of the Whipple shield itself. Traditionally, a key material of the Whipple shield is aluminium 6016T6, which is ideal for this process, and this alloy is found in abundance in space debris. By applying the finite element method in Abacus and using heat transfer tools, we are optimizing the cooling rates of the Mamba process, refining temperature transitions to retain the material strength and durability. This ensures that the captured debris can be transformed into high-quality Whipple shield components. With this approach, we're not just cleaning up space, we're building a future where space sustainability is fully self-sustaining.
As mentioned previously, the total value of all debris in space currently orbiting could be as high as $1.2 trillion, which is equivalent to the 18th largest GDP globally. Walls has a particular advantage being an early mover in the industry, with only a few competitors and no competitors in the exact sector that we're working in. Our primary revenue stream is going to be bespoke parts made for in-orbit servicing. This is particularly attractive to companies due to the lower cost compared to launching things, smaller time frame of delivering the parts, and better sustainability, especially in an industry where now the lifespan of satellites is looking to be increased further and further. As a secondary revenue stream, we're looking at disaster response for when collisions occur in orbit. We can mitigate the effect of the collision and reduce the amount of debris in space. And we are looking to collaborate with international organizations and governments to make this a reality and to appeal to the existing space industry.
Track, capture, remanufacture. That's our mission here at WALS. We're pioneering the first environmentally friendly space debris solution. Unlike current methods that harm the ozone with debris re-entry or push it into graveyard orbits, we capture and remanufacture it directly in space. Using a sweeping shield structure, we safely collect debris traveling at hypervelocity, then transport it to an unmanned space station for processing. Instead of wasting valuable materials, we recycle them to build new capture systems, creating a self-sustaining cycle of space depollution. Our innovation tracking system ensures real-time detection, while electric propulsion optimizes long-term orbital operations. With debris valued at up to $1.2 trillion, our solution isn't just about sustainability. It's about unlocking a new frontier for space manufacturing and repair. WALS isn't just cleaning up. We're revolutionizing how humanity interacts with
Space!